I'm going to be talking to you a little bit in this video today about data exploration in R from a beginner perspective. The plot and tables you see on the screen here are things that you could do pretty easily in SPSS. And we're going to talk about how to create these kinds of things in R. And we're going to use a few different packages to help us do that, and I'll talk about how to install them in a moment. But the packages, we're going to use our Rio for easier importing of data. We're going to use the Ggplot 2 package to help produce nicer looking plots. The psych package to be able to get a bigger range of descriptive statistics with a single line of code, and then the car package to help do some things to do some assumption checking a little more smoothly. So I'm going to give you a second to get our studio pulled up, and then we'll begin. All right, so we're going to be using data from a guy that uploaded data from his own roller coasters in the game Roller Coaster Tycoon, and he put this data set on Kaggle. I'll put a link in the video notes. And so from this data, one question that we could explore is a question: are there differences in average nausea level across roller coasters with different excitement ratings? And I have a similar video about this using SPSS, so if you want to, you can go check that out as well and see how to do these two different things in each different program. So to start with, you're going to need to install a few packages if you don't already have them installed, and you're going to do it by using this first line of code here. So in this case, install.packages and put ggplot2 in quotation marks. And you're going to need to do that for Rio, for psych package, as well as for the car package. So pause the video for a second, make sure you install all of these packages, and then we'll go on. So the next thing that you should do is set the working directory, and this is the file path that leads to where the roller coaster's data file is stored. So I'm using a Mac, so the difference here might be that these are turned around backwards, and make sure that the C colon is at the beginning of your file path in order to ensure that the line of code here is taking you to the right place. And then you'll notice that the file is actually an SAV file. That is a file format for SPSS, and this import function is a Rio function from the package Rio that it will automatically recognize the type of file that it is and import it correctly. And so I'm using this left arrow here in order to say store the file in the letter D. So once you're ready to do this, you need to click through each of these and run the code so that it activates all of these files, or all of these packages, and then imports the data. So you can do this by just going and putting the cursor at the top line here and clicking Control Enter or Command Enter on a Mac and run these lines. So once you start doing this, you'll start to see that it's allowing all of these packages to be activated for use. I'm going to set the working directory, import the file, and you'll see that it did work. There's a blue arrow here and no errors, so seemingly it worked. But let's check it by looking at this names function, which will tell us the variable names that are in the data set. And we want to make sure that things look correct here. So we have things like park ID, theme, roller coaster type. And we can also look at the structure of these. And so what I mean by that is are each of these variables a set of character values, which means it's just text? Are they numeric numbers? How were they imported when they're imported? Because some of the things we're going to do require numeric values. Some things require factor level variables, and so we'll have to deal with that here in a minute. But if we look at the structure here, scroll up a little bit, you can see that the very first one, park ID, it says is numeric 0, 1, 2, 3. The theme is CHR, that means character. So you'll see these different themes. Barony Bridge is the first one that's listed. You'll see the variable roller coaster type is a character. So here we have bobsled coaster, dinghy slide. And so these are different categories we could disaggregate the data by, but we would need to turn this into a factor variable. And the variables of interest that we're going to talk about in this video, in this question that you see on the screen, is about nausea and the different excitement ratings as categories. So what we're hoping to see then is that nausea is a numeric variable. So if we scroll down, here's nausea, and it is numeric. You can see it has variable or values with up to the hundredths place in decimal format. And then excitement rating is here, and it is listed as a character variable with values of high, medium. There's also a low and a very high value in here. And so because those are characters and we want to separate them out by groups, and in the SPSS video, I talk about how the word factor means group by, or the groups that we are comparing across. And so that's why this next line of code, I use a hashtag here for a comment so that our program knows not to do anything with that and view it as a set of actual functions to run. So we want to change excitement rating variable here to a factor. So the way to do this is first you want to type in $, excitement rating, and that dollar symbol tells our environment whatever follows it, that's the name of the variable. And as you start typing it in, you will see it come up. So $, as I start typing, it starts to come up, and I can just arrow down and hit tab, and it will input the rest of it for me, so I don't have to type it all. And then you want to type a function. So first of all, this means store into. So we want the excitement rating variable to be replaced by this new factor variable. We want to just change it to a factor. And so we use this function called as factor, meaning change it to a factor. And then, of course, you have to put inside the parentheses here the thing that you want to change to a factor variable. So excitement rating. So once you've typed that in, and I can now give us a little more space here, I think we'll be able to see. We can go ahead and run that. And when you do that, it's hard to tell, did it actually do anything? So one thing we can do is look at the structure of just that specific variable, the $, excitement. So str will tell us that, and this time we don't want to look at the whole entire data set, so we can just put excitement rating in, and we can see it says factor with 4 levels, high, low, medium, and it doesn't show us all of them. So if we want to see all the levels, we know that it worked. You can just type levels with $, excitement rating in parentheses there. And that will show you that you have high, low, medium, and very high as the different levels. So basically it took each of those words and made it a factor or a category made them all categories of that variable so that R views those as specific categories. So the next thing to do is to run some summary statistics. This would be the first thing you would want to do in SPSS using the explore option perhaps. And a base R, which means not using a particular package, function you can run is just simply summary of $, nausea. And at this point, we're not grouping nausea by these excitement levels, but I just want you to see what it looks like. So if we run summary of $, nausea, it's going to give us basically the 5-number summary as well as the mean. And so these are the values that you would see in a box plot, for instance. So you get the minimum, the first quartile, the median, the third quartile, and the maximum, and it also shows you the mean. And that's for the entire database. Now, we're going to use something in the psych package because it's going to give us a different or a more extensive set of descriptive statistics, similar to what it shows you in when you run explore. So if we use the word describe $nausea, it's going to give us the number of data points, the mean, the standard deviation, the median, the trimmed median, the mean absolute deviation, the minimum, the maximum, the range, and also skewness and kurtosis values, and the standard error for the skewness and kurtosis. And so the important thing to notice here is that you get the mean and the median, as well as the standard deviation and the mean absolute deviation, minimum max. Like that is the same kind of thing you're going to see in SPSS. And we can look at these skewness and kurtosis values here and start to make judgments about whether or not we're going to have any issues with normality. A really helpful way to do this is because we're going to be looking and comparing across these groups is to see these statistics broken out by groups. And so also within the psych package is a function called describe by, in which we can put the second input into our function be the grouping variable. So we're describing nausea by excitement rating. So if we run this line, it's going to break this out by each of those. So here we see group high. So at the high group, and an important thing to notice here is the N. So on the high group, we have 116 nausea rate values. The low group, we only have 2. And this is going to cause us a lot of issues later because it's so small and it becomes difficult to even interpret how useful a mean is, and comparing differences between that group and another group. We'll have to make a judgment about that later. Medium group, we have 12 roller coasters in that group and 12 in the very high group. So there's a very big difference in the number of roller coasters that are included. So if we were wanting to think a lot deeper about this, we either would want to try to choose something else to separate things by, because it seems like there's not very many, most of the roller coasters have high excitement values, or we'd need to think about combining some groups and reducing the number of groups that are here. But we're going to continue like this just for purposes of now in order to start to make sense of this. So in thinking about normality tests, because there's only 2 in this low group, we actually can't run a normality test for that. There's actually not any reason to even have a histogram for that because there's only 2 roller coasters. There's literally 2 data points. So making sense of normality for that doesn't make sense at all. But if we look over here on the left side again, the way to do this, the easiest way to do this, actually, there's a lot of other things you might see if you start searching on how to do this with other packages, or to do it by group to make it sort of 1 or 2 lines of code to do all of it at once. In this case, because we have 2 here, these functions actually won't run. You need at least 3 data points in order to run these. So the way that you can get these to run, there are 2 types of tests, and these are also things that are printed out in SPSS, is the Shapiro-Wilks test of normality and the KS test for normality. So the Shapiro test is just Shapiro.test. And the way that we want to pull out just those groups, so we'll start with the medium and skip over the low, is $nausea, and in brackets, we're telling R which things we want to pull out of the nausea list. So we're telling it to only include $, excitement ratings that equal the word medium. And in R, you need 2 equals signs in order to mean the same thing as equivalence in mathematics. So we're using two equal signs, and basically, so if you just run this first one, you'll see this pop up here, and it will show you the Shapiro-Wilks statistic is 0.95, and the p-value is 0.6936. And remember, Shapiro-Wilk and KS test, the null hypothesis is that there is normality. So if we're not rejecting that, then we're saying there's not enough evidence to say it's not normal. So we're going to assume that it is normal. And I hope that makes sense. So what you can do then is just simply copy and paste this and change the word to high and then change it to very high to get a look at what these tests are telling us. So I'm going to run these here. Feel free to just pause the video here and do it yourself. But with the high group, which had 116 roller coasters, there is an issue with normality. And we'll also look at some plots here in a minute, and maybe we'll notice why. And then with the very high group, there also seems to be an issue with normality with a p-value smaller than 0.05, meaning that we're rejecting the null hypothesis, which says everything's good, it looks normal, and we're saying no, it doesn't. Things seem to have deviated beyond that. We could also run the KS test just as a second check on these, and there's one addition that we have to make. So basically it's the same as the Shapiro test with this bracket where we're telling it to only look at medium, then look at high, then look at very high. But we also have to tell it which distribution function to use. So this tells it to use a normal function. And if we run these, you'll see that it appears to be showing some issues with normality with the medium group, and with the high group, and with the very high group. So this is telling us something a little different, and so we're going to have to make a judgment here. In general, the Shapiro-Wilks test does have a little bit more power, so I tend to default to that one as opposed to the KS test for these kinds of sample sizes, at least. So let's move on and then talk about the plots. How do we get the same kinds of plots you would find? So for normality, we care about the histograms, and we also might care to look at the box plots just to compare across these groups and get an idea of an initial sort of expectant answer to our question about whether there's differences. Box plots are really helpful for that. So we're using the package Ggplot 2. In this, you could do some of this in base R as well. To me, it's just a little more complicated to do so. So Ggplot, what you do is you always start with the function Ggplot, and then the first thing you enter in parentheses is the name of the data set. Then you follow that with AES and open parentheses, and AES means aesthetic, so you're adding something to the plot. So you're telling it the data set that you're pulling from, and now we're going to tell it that we care about seeing the excitement rating and nausea value. And then close both sets of parentheses so that you're closing the entire Ggplot line, and then a plus symbol. So the way Ggplot works is you first tell it some really basic thing, and then you add elements to the plot. So in this case, we're going to say plus and then hit the enter key, and then just simply put in geom boxplot, geom underscore boxplot, open and close the parentheses. In this video, we're not going to dig into how to make this look super pretty. We will do that a little bit later in some other videos. I'll have videos just about that at some point in the future. So and you just have to put the cursor on the first line and hit Command Enter or Control Enter, and it will run both of those. The plus symbol tells it you're not done yet with that function. And once you do that, you'll see the plot show up. Eventually, it's taking a little bit for it to show up here. There we go. So it put excitement rating along the bottom. That's because excitement rating is the first thing we entered. So that is the x-axis. Nausea, it's implied that that's the y-axis. So if we look across these, it looks like there's differences between these groups, and maybe not so much difference between the high and the very high group. But perhaps the medium and the very high and the medium and the high group, maybe there's some differences there. The medium and the low groups definitely have lower levels of nausea, it looks like, especially if you're just looking at that median value. But remember, Anova tests differences in the means. So there might be some differences there, but it looks like maybe we'll have some significance in our Anova test later. And another thing that we want to do is look at a set of histograms, because we want to also look at the normality again and check that against what we saw with these normality tests and the skewness and kurtosis values that we examined previously. So once again, Ggplot, and you're going to put in D, and this time only put in nausea. And the reason for that is we're going to use a function called facet wrap that creates a series of separate histograms, but all in the same scale, so that we can see them together, kind of like this does. But if we did what we did up here with the Ggplot to create the box plot, it's not going to work the same way with the histogram. I think it's easier to see it in sort of a table format. So just put nausea there, and then close the parentheses, plus, and then type in geome histogram, open and close parentheses, plus. And then here's where we tell it that we're going to facet wrap means that we're going to create separate plots for each of the levels of excitement rating. And notice there's a tilde symbol at the beginning of the excitement rating. In R, the tilde means by. So we're going to facet wrap by excitement rating levels. So put that in there, and then we're going to click Command Enter or Control Enter and run that line of code. And this little piece in red here is just telling us that reminding us that we can change the bin width, how wide the bars are on the histogram, if things don't look very good. And now we're waiting for my processor to catch up. All right. So this is the high group. It does look like there's a little bit of skewness to the right, which indicates that maybe we have non-normality. Of course, there's the low group. The medium group, you can see how spread out it is. That's why it probably is telling us we may want to pick different bin widths, although the bin widths look good for the high group. So if we were going to change bin widths, we would need to do that within each group. And then the very high group, you can see how spread out it is, because there's only 12, remember, in each of these two. And so that also looks a little bit skewed. So that may be why the KS test was throwing us non-normality problems, although the medium group looks fairly symmetric. And of course, another thing that we should check is the QQ plots. And remember, these are plots that tell us whether or not it compares the distribution that we have to what it would be if it was perfectly normal or perfectly symmetric. And so the easiest way to run this actually is using the car package. And it's simply a function called Ggplot, and notice that the P is capitalized. And then we're going to use this tilde again to say, give us a Ggplot that shows nausea by excitement rating, so that it produces Ggplots for each different level of excitement rating. And then the comma D at the end is telling it what the data set name is that nausea and excitement rating come from. So once you have that in there and you run that code, we'll see all 4 of those plots show up. And it's taking a minute to generate them all. And we're waiting on the very high one. There it is. So you can see here, if we make this bigger, it might be a little bit easier. It looks like the high group has this point way up here, case number 129, row number 129, that falls pretty far outside and outside of these lines here, which give us there, it generated it finally. That give us where things should fall within before they become out of bounds. So that 129 is kind of out of bounds there. If we look at the medium one, 58 and 34 appear to be a little out of bounds. And the very high group, it largely is within bounds, but it's kind of all over the place and doesn't really follow much of a linear trend. So there could be some issues there, but because there's so few data points, it's hard to really tell. But we have this, and by the way, you can export these and save the images to put in a paper or something, for instance. And then, of course, some other things that we'd want to check for assumptions are also a test of homogeneity of variances. And one way to do this would just be to first check the standard deviations, see if they all look really similar to one another, because that is an assumption of Anova. And this test, Levine test, is a base R test, and we can simply say nausea by excitement rating again using that tilde. And then we want to tell it to use mean as the measure of center because by default it uses the median, but Anova uses the mean, so we want to check that. And then make sure to tell it that the data equals D, the data set, that, or if you called it something else, whatever you called it. So we want to include those things. And then if we run this Levine test function, we'll see that the p-value here is 0.5926. And the null hypothesis for the Levine test is that variances are equal. So we're not rejecting that, which means we're assuming that variances are equal, or that at least we don't have evidence to say they're not equal. So now we are finally to the actual Anova test here. And the way that you run an Anova in R is, with base R, is the AOV function. You would think it would be Anova, which there is a function for that, but that's not the same thing. So we're going to call AOV, and then we're going to say D dollar nausea by D dollar excitement rating. And when you do this and run that code, you'll notice that it doesn't give you any p-values or f statistic. To get that, you have to run a function called summary on that Anova result. So you can just copy and paste this in a set of parentheses inside of the summary function like this. And then we will get the same thing, but now we have a p-value and an f statistic to go with it. The f statistic is 4.146. The p-value is 0.00755, rounded, of course. So p is less than 0.01, which means statistically significant. And what we don't know is where it's statistically significant, because remember, there's 4 levels here: low, medium, high, and very high. So what the Anova test is doing is looking across all groups and saying, okay, there is statistically significant differences across those groups. In order to actually know where that is, we would have to run a post hoc test like Tukey HSD, which runs a pairwise comparison of these. You could also run Bonferroni like this. And so if you haven't saved this AOV into something, so you could, for instance, put Anova roller coaster, right? Anova is a function that already exists, so you don't want to use the same one. So if I type Anova roller coaster and use an arrow, then I could have everything stored in this variable name. For this purposes, I'm just I'm not really doing anything complicated. So you can just copy and paste this and type Tukey HSD, and inside of that put the Anova that we ran, and it will show you a pairwise comparison across those. So the low versus the high group, the difference between those, and it is subtracting low minus high, just like it looks like it's showing here, is -2, meaning that the high group had a larger mean nausea level than the low group. And here's the p-value, and this means lower and upper of the confidence interval. So this is the lower end of the confidence interval, and this is the upper end, and these are 95% confidence intervals. That's the default, and you can see that up here, 95% confidence level. So the p-value here, it's less than 0.1, but not less than 0.05. So depending on what cutoff value we want to use for alpha, we could call this statistically significant difference between low and high. The only other place that we see statistical significance is in the last two, though, which is the very high to low group and the very high to medium group. And if you remember on the plots, if we go back to, if it lets me go back here. It's just taking a while to load them. So you could compare this back to thinking about those box plots or the histograms. Here's the box plots. And so we had some some thoughts about this low and medium group compared to the very high group or compared to the high. And it turns out that medium and low do have statistically significant lower nausea levels than the very high excitement roller coasters. At least they are statistically significantly less. However, there seems to be not the same difference between the high groups. So medium to high, very high to high, those produced p-values that are pretty large, and a case could possibly be made for high versus low, but not high versus medium, which is interesting to see that. And I think it has to do with this variance here that exists. So so that's how this works with R, and hopefully you learned some things, and feel free to ask questions and keep learning about R.